Hello, this is Richard Ignis in the Department of Physics and Astronomy. Today I'm going to talk about radioactive decay and the half-life. Radioactive decay refers to how a nucleus can undergo an adjustment. It can actually change its elemental type. Different kinds of decays are discussed in the textbook and in lecture. Here my focus is on the concept of the half-life, which describes how fast a nucleus undergoes these transitions, and to do some example problems using the half-life concept. So here's an expression that involves the half-life. The idea is we have a certain amount of substance, which I'm going to label with a capital N. And the convention is to refer to the original material as being the parent. And after a decay takes place, part of the parent changes into, again by convention, material known as the daughter. So the amount of the parent substance, is capital N, is equal to however much you start with, which has a subscript 0, and then, depending on how many half-lives have occurred, you take 50% of that material for each half-life. Okay, so that's the equation. Let me kind of express this in word terms. So the parent amount, I'm going to abbreviate amount here, is equal to the original amount. I'll also abbreviate original as well, multiplied by a 50%, what you might call an attrition factor, but raised to a half-life count. Now that's a power. So the idea here is that with the passage of every half-life, however long that is, with the passage of every half-life, you have half as much as what you had at the previous half-life. Now, before I go through an example, let me write down the amount for the daughter product, or the daughter amount. We can also write an equation for this. The amount of the daughter, using subscript D, is equal to whatever you started with, the original amount, minus the parent amount. So when we start, the parent amount is the original amount, and there is no daughter. So this would be 0. But as time progresses, with the increasing of time, there's some fraction multiplied by the original to represent the parent. So that means that as the parent decreases, the amount of daughter product is increasing. We can also write this in words. The gain of the daughter amount is equal to whatever the loss is of the parent. All right. Let's go ahead and step through some examples. Now, for the examples that follow, do the first one here. I'm going to use a real substance as the example. There's a material called potassium 40. The 40 here refers to both the proton count and the neutron count. This can be written in shorthand. K is the elemental symbol for potassium, so 40K. Now, potassium 40 can decay into argon 40. Symbol is there. Notice that they have the same number of protons and neutrons. The total count here is a 40, but the element type has changed. So the number of protons have changed. So I'm not going to talk about that in detail. All I want to point out is if we go back to this expression here, when we talk about the half-life, how many half-lives, there's a characteristic time for each kind of decay, whatever elements that we're talking about, over which they change from parent to daughter. At that time, we usually give the symbol Greek letter tau. So it's an amount of time in seconds, days, or years, depending on what the substances are. In this example of the decay of potassium-40 to argon, the time scale here is 1.28 billion years, or 1.28 gigayear, using the metric prefix, or in scientific notation, 1.28 times 10 to the 9 years. Now, initially, we're not going to worry about the time amount. We're not going to ask the question about how many years, but we will come to that. Here we just want to illustrate how this half-life works. So the question is, how much potassium and argon are present? How much potassium and argon are present after 2 half-lives? And what we're going to do is we're going to find either percent or fraction. So let's work on the potassium first. If we have 2 half-lives, after the first half-life, we have half of whatever we started with. We don't care how much it was. Was it a kilogram? Was it a ton? Was it a boulder? It doesn't really matter what it is. All I know is that after 1 half-life, we have half of it. After the second half-life, we have half as much as that. So one potential problem or misconception with half-lives is to think that you lose half in the first half-life and then you lose the remaining half in the second half-life. But that's not true. What you lose are successive fractions. That means products. So half of a half is 1/4. So there's 25% of potassium remain. Okay. Well, right away, if the growth of the daughter depends on the loss of the parent, if only 25% of the potassium remains, 75% has been lost. So it must be 75% of the sample has been gained in the form of argon. So that's our first example. That's how much is built up. The sample has 25% of potassium remaining, but the gain in the argon has been 75%. So it's as if the sample is transforming right before our very eyes. Let's do a second example. Let's change this just a little bit. Suppose instead of asking the amounts, turns out we'll still have to find them, but instead of asking that as the outcome, the actual separate amounts, we ask for a ratio. Suppose we ask, after 3 half-lives, so that's 3 tau, 3 times tau, 3 half-lives, changing up how we represent it here, what is the ratio of potassium to argon? It's really the same basic question. We're just kind of changing the look of it at the end. And I'm also going to change the look of how we go about it. I'm going to start using that formula now. What we do is how much of the potassium remains. We take the 1/2 and we raise it to the count of half-lives. How much time has passed? Well, there's some number of years. Whatever it is, it's 3 times the characteristic time, the half-life amount. For potassium, that was 1.28 billion years. So almost 4, 3, pushing 5 billion years here, of 4 billion years, but the point is that the power is a 3, so it's a cube. That's 1/2 times 1/2 times 1/2, and the number I was looking for was close to 3.78 billion years, but that's 1/8. So the amount of potassium remaining is 1/8. The amount of argon that has been gained is 1 minus that. That'll be 7/8. So the ratio, we have to make sure and double check here, what are we ratioing, who's on top and who's on bottom. So in this example, the potassium is on top, the argon is what we're putting in the denominator. So we have 1/8 is the potassium relative to the argon, which is 7/8, and that's 1/7. In other words, the amount of argon present in this sample is 7 times greater than the amount of potassium. Let's just do one more problem. This one is going to involve the actual time element. Here we've just been talking relative half-lives. Let's actually get to years. When you try to turn it around, and you ask questions like, I started with so much material, I have so much of the parent, or I have so much of the daughter, or however it is presented in that way in terms of the quantity of material, and you try to go back and figure out, gee, how much time has passed, that problem can be a little bit more challenging, but it's often good enough to make an estimate. So that's how I'm going to go about this example. Now, suppose we have 1 gram of sample material. Doesn't matter how we got it, but we have the sample and it has a mix of the potassium and argon. We're still working with those. Imagine that at this time, today, or whenever it was analyzed, 30% is potassium. Of course, that means that 70% must be argon, right? 70% is the argon. It's not really what we're asked, but that's okay. But 30% is potassium. So the question is, how much time has passed? How old is the sample? It's a question of age. It can be a little bit tricky in terms of how the sample was acquired and the conditions prior to that, but just straight up, let's just say if we got 30% potassium and the sample was all potassium to start with, argon, the daughter product, has grown in amount over some period of time. The question is, how much time has passed? So we have to turn the equation around to solve for time. As I said, that can be a little bit challenging. It would involve logarithms. Let's go the estimate route. How many half-lives have passed? Well, if it were 1 half-life, okay, then we would have half the material, or 50%. And that would be 1.28 billion years or gigayears. If it were 2 half-lives, we would have 1/2 of 1/2, which is a quarter, or 25%. And the amount of time that would have passed is twice the 1.28. So that's 2.56 gigayears. Since we have 30%, the amount of time that's passed for this sample must be between the 1.28 and the 2.56. 30% is closer to 25 than it is to 50%. So if I just had to estimate, I would say that the sample is around 2 to 2.5 billion years old. And that completes the examples that I wanted to go through for how to use the half-life to figure out amounts given the passage of time, or provided with amounts, how much time has passed.